All right, we're going to start looking today at inference for distributions of categorical data is what the title of the chapter is. You're going to probably be thinking to yourself, wait, we've already done that. Isn't that a one prop z-test? Didn't we already look at categorical data and how to do significance tests and confidence intervals for categorical data? This is another way to do it when we want to do multiple tests at the same time. So you could kind of think of this chapter as chi-squared, or some people call it chi-squared. So that's what this chapter is really about, chi-squared. It has this funny symbol that looks like that, like a fancy italicized X squared. So the chi-squared is what we're going to be focusing on in Unit 11. And really what it allows us to do is multiple one prop z tests at the same time. So if we want to test if something is uniformly distributed, meaning is it the same, is the bag of M&Ms to have the same amount of reds, blues, greens, yellows, whatever colors in there? Are they all equal? Well, we would have to run a test for red, a test for blue, a test for yellow, a test for brown. What chi-squared allows us to do is to run one test for the entire population. So it's very beneficial and saves us a lot of time in the long run by using chi-squared. There's three different reasons we would use chi-squared, but the process is going to be the same. When we do a significance test, we have 4 steps. What are we going to do? Are we allowed to do it? Do it and tell us what the heck it means. Same for chi-squared. We're going to have the same 4-step process. So you're probably getting tired of this by now. It's like the 4th chapter in a row. We've been doing the same thing, but you can see the importance of significance testing and confidence intervals when the book focuses on it so much. It's a big part of what we're doing in this course. Okay, so let's get started. Here is a bag of M&Ms. Okay? We went to the store, randomly purchased a bag of M&Ms, and there was 12 browns, 3 reds, 7 yellows, 9 greens, 9 oranges, 20 blues, and there was a total of 60 M&Ms in our bag. Okay? This is what we will call the observed. That's what we observed in our bag of M&Ms. So the book will refer to this a lot, excuse me, as the observed count. How many did we observe? So the observed, pretty easy to determine what that would be. We just simply look at what we found. So we open up the bag and we count how many there are. Pretty simple. Okay. Now, we needed to figure out how many did we expect to have. So they claim, the M&M company claims that 25% of their candies are blue, and they claim that they make 25% of their candies to be orange, and they claim that 12.5% are green, 12.5% are yellow, and 12.5% are red, and 12.5% are brown. That's the company's claim. Okay? Notice that these percents must add up to 100. Okay, so their claim is, hey, 12.5% of all the M&Ms that we make are brown, 12.5% are red, yellow, and green, and then 25% are orange, and 25% are blue. So we need to figure out how many candies we expected to be each color in the bag. So how many did we observe? How many did we count? It's given up here in this top table. How many did we expect? Well, if there was a total of 60 M&Ms in the bag and we expected 25% of them to be blue and orange, we would have expected there to be 15 blues and oranges. That's what we expected to happen. And then we could figure out how many browns, reds, yellows, and greens we expected by doing 60 times 0.125. Oh, we expected 7.5 of the candies to be brown, 7.5 to be red, 7.5 to be yellow, and 7.5 to be green. So that's where we come up with this expected count. Okay. What is the hypothesized percentage? What is the claim? They tell us this is what we did. And we're going to test to see, I don't know if I believe you guys or not. Okay. So is the distribution of M&Ms as the company claims they are? So first, we need to figure out what are the observed values, and they are simply what's given to us in the problem, what we found in the bag of M&Ms. Okay, and how many do we expect? Well, we take the total times the claimed percentages. That's where we got this expected from, and here's our observed right here in this first column. Now, down bottom, we made a graph, a side-by-side bar graph of the distribution. Remember that chi-squared is for categorical variables. Okay, what color is your M&M? Brown, red, yellow. It's categorical. You can't answer that question with a number. All right, so you can see that the blue bars here are the observed counts. That's how many we actually counted. And the red bars represent how many we expected. So looking at the differences between these blue and red bars, is this evidence that they're not telling us the truth? What we need to say, what we need to be able to do it by the end of this is come up with a p-value and come to a conclusion. Do we believe their claim or not? And looking at this, I'd say, well, the browns were pretty different from what I observed, from what I expected. The oranges were quite different. So were the blues. The yellows and greens, they look like they were pretty close to the claim. Okay? But is this difference enough to be statistically significant? There's clearly a difference. It's not exactly as claimed. And it couldn't be, because it's okay to have expected values that are decimals, 7.5. Well, we can't have half an M&M. Either we have the M&M in the bag or we don't. So expected counts won't always be whole numbers, and that's okay. Right. So now that we understand what is observed and what is expected, we should be able to move on to calculating the test statistic. So remember, before we would find a z-test statistic, a t-test statistic. Well, now we're meeting a new test statistic, which is called the chi-squared test statistic. Okay? And this chi-squared test statistic, the formula that's going to be in your formula packet that you're going to be using for all your tests, is going to say the summation of the observed minus the expected squared divided by the expected. What is this summation? It means do it for every single point that we have there. So we need to do the observed minus expected for each and every color of M&Ms that we did earlier. I'm going to rewrite this formula just to simplify it slightly. And I'm going to say it's the summation of O minus E squared over E, where O stands for observed and E stands for expected. Okay? And then we have to find the sum of all of those values. So let's actually calculate a chi-squared test statistic here together. Okay? If we look at this problem in blue here, okay, Carrie made a 6-sided die in her ceramics class and rolled it 90 times to test if each side was equally likely to show up. The table summarizes the outcomes of her 90 rolls. So down here, this frequency, the table that she wrote down, is her observed. When she rolled the dice, this is what happened. Okay, so though we already have the observed counts. Remember that for every single test that we do, any significance test in the world, the null is always there is no difference. So here they'd like us to state the null and alternative. So instead of writing it out the way we have before, we might, in this case, want to write the null and alternative in words. So the null is there is no difference, meaning the sides of Carrie's dice or die, since it's singular, are equally likely. There is no difference. Her die acts the same as any fair die. So they're equally likely to show up. Where the alternative might be that the sides of Carrie's dice or die are not equally likely to show up. So what are we really saying? We could write it like this and say that the proportion of ones is equal to the proportion of twos, which is equal to the proportion of threes, which equals the proportion of fours, which equals the proportion of fives, which equals the proportion of sixes, and they all equal 1/6. Because if they are equally likely, then the proportion of times that each number would appear would be 1 out of 6. And then the alternative would be at least one proportion is not 1/6. So you can see here, we could do a one prop z-test and test that P1 equals 1/6, and then do another test, and then do another test, and until we've done 6 separate tests. That would suck. You've seen from the last few units how much effort it takes to perform a significance test. And to run 6 separate tests, we'd have to do the 4 steps 6 different times. That'd be a lot of work. That'd be a very, very laborious task for us. So what chi-squared is going to allow us to do is to run this test for all of them at once. So we'll erase this and look at this that we have here as the null and alternative. But I just wanted to show you what we're really doing. But we don't have to necessarily write all of that out. Okay, the sides of Carrie's die are equally likely to show up. The sides of Carrie's die are not equally likely to show up. I guess I should make the English teachers happy and put a little comma in there or an apostrophe in there. So part A would like us to state the null and alternative. So we've done that. So part A, state the null and alternative. Part B asks us to calculate the expected count for each of the outcomes. I like to write expected right underneath the observed. Just makes it easier for me. This frequency is really the observed, right? That's what we saw happen. We observed that. Now, how do we find the expected counts? We take the hypothesized proportion times the total. So for the expected, each one, we expected it to show up 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. So if I take 1/6 times 90, I can get my expected counts. So my expected would be 1/6 times 90. Well, I can make 90 into a fraction and make it 1/6 times 90 over 1. So it would be 90 over 6. If I wanted to reduce this, it could be, how many times does 6 go into 90? Oh, that's 15. So I expected 15 times each number would appear if the die were equally likely. So if the null hypothesis is true, what do I expect to happen? So that's how we find our expected values based off of the null hypothesis. We expect there to be 15 of each. Calculate the expected count for each possible outcome. So this here would be our answer for B. Now they'd like us to calculate the chi-squared test statistic. So they want us to calculate this chi-squared. So remember, it's the summation of the observed minus expected squared divided by expected, plus the next observed minus its expected squared divided by expected, plus the next observed minus expected squared divided by expected, plus the next observed minus expected squared over expected, plus the next one, 10 minus 15 squared over 15, plus the next one, 15 minus 15 squared over 15. So I could take my calculator and do this would be 12 minus 15, that's 3, 3 squared is 9. So the first one turns out to be 9 over 15. So this one is 9/15. Okay. This would be 13 over 15 squared. Okay. 13 squared, that's a pretty big number here. That's going to give us 169 over 15. This would be 9 over 15 once again. This one would be 4 over 15. This one would be 25 over 15. And this one would be 0. Now I need to add all of those together. So that's going to give me, if I add up all of these fractions together, they all have a common denominator of 15. So these two together make 178, 187, 191, plus 25 would be 100 would be 216. So my chi-squared would be 216 divided by 15. So 216 divided by 15 gives me 14.4. So my chi-squared test statistic would be 14.4. Now, that's a lot of work, especially if we have more than 6 or more data points than this. Let's take a look at a way that we could do this easily in the calculator. Our lists are going to be our best friend in here. Our lists are going to make things so much easier. So let's go, remember lists, we go to Stat, Edit. I'm going to clear out this list, and L1 is going to equal my observed. Whoops. So let's make L1 equal to observed. So I'm going to simply type in my observed roles. Yep, I have 6 points in there. I know I got them all. Now I'm going to put my expected into list 2. And I already figured out that my expected was 15 each time. Okay, so let's say L2 equals our expected values. Now let's let the calculator do all of this calculations we did here by hand. Let's let the calculator do all that for us. So if I go over to list 3, remember, if we want to put a formula in, we have to make sure that we've highlighted the heading up at the top. I want that to do the formula, which is chi-squared equals the summation of O minus E squared divided by E. Oh, well, O is list 1. So I'm going to say list 1 minus the expected, oh, that's list 2. And I want to square that, and then I want to divide that by the expected. Oh, expected is list 2. Now that did all of the calculations for us. It put them in decimals instead of fractions, but that's fine. And then finally, I need to do this summation part. So remember, if we go back to the main screen, we go to second catalog, I'm going to go to T, and then I'm going to go up to summation, or to sum. So I'm going to tell it to sum, and the calculator's like, cool, I'll add for you. What do you want me to add? I'd like you to add, please, all the numbers in list 3. Oh, so the chi-squared value is 14.4. Beautiful. So we can let the lists do all the work for us instead of us having to write everything out like we've done here when we did this problem by hand. So if you can figure out how to manipulate those lists, you're going to be much happier and save yourself lots of time throughout this course. All right, so now we know how to state hypotheses, how to figure out the expected count, and then actually calculate the chi-squared test statistic and the formula for that. So what is the chi-squared distribution? It's clearly not normal. The chi-squared distribution is defined by degrees of freedom. Hey, we've heard degrees of freedom before. Remember, for the t distribution, there was degrees of freedom because the curve wasn't perfectly normal. If you recall in the t distribution, here would be our perfect normal curve, but the t, depending on the degrees of freedom, looked more like this, or it would look more like this one, or it would be something like this, depending on the degrees of freedom. Well, chi-squared acts the same way. Chi-squared is with a small degrees of freedom, is an extremely right-skewed distribution. Okay. But as the degrees of freedom increases, so as n gets bigger and bigger, what happens to every curve in the world? It starts to become more and more normal. That's also true with chi-squared. Because of this special distribution that chi-squared has, we need a new table for it. And in your formula packet, this table, if I can grab a hold of it and bring it over here, is called table C. Okay, so where did there we go. Now I got it. Okay, so it looks like this. You can see the chi-squared symbol here, the chi-squared critical values, and it behaves just like the T table did. But the numbers in here are much different. But we have degrees of freedom, and we will have a chi-squared test statistic, and we'll trap it between two values and come up to the top here to calculate our p-value. So we have an idea here of what the chi-squared distribution looks like. As n gets larger, it starts to become more and more normal, but it's definitely not a normal curve to start. Therefore, we need another table to be able to find the p-values that are based off of this.